In this lesson, we're going to store a bit. A bit. You think about it. Wait a minute. I need to store a lot more than just a bit, but it's got to start somewhere, right? Well, way back in the late 40s, there was a project called the Manchester Baby, or the Manchester Small Scale Experimental Machine. And what it had was a cathode ray tube that had a grid of 32 dots and dashes. And I'm not going to draw the whole thing here, but basically this grid of 32, it was 32 rows by 32 columns. So each row was a 32-bit number. Okay, and a dash represented a positive value, and the dot meant a negative or charge. And there was this grid behind it that determined whether or not there was a positive or negative charge on each one of those positions, so it could in fact maintain data. That's pretty old school. It was really cool in that you could actually see memory, but if you can see memory, heck, it's not all that small, and you won't be able to compact all that much data into a small area. Now, later on, they developed something called core memory. Now, we talked a little bit about this idea of if you send current through a wire. So based on the right-hand rule, if you send current in a direction in the wire, you're going to get an electromagnetic field around that wire. Now, the idea was if we took this ferrous or iron-based kind of little bead and put it so that there was a wire going through it, if you send enough current through there, you could magnetize this little bead. Now, the problem was getting an array of these so that you could actually program or set the magnetism in each one of these beads. And the way it worked was, well, they put basically a grid of these, and you sent wires, so there were rows of these beads and there were columns of these beads. And so one wire went through a column of beads and another wire went through a row of beads, and you had this mesh. It was actually quite beautiful to look at. And what would happen is you put 1/2 of the current that it took to magnetize this bead on the vertical of the column where the bead existed that you wanted to program, and you put the other half of the current going through the other way, so that where they crossed, and I probably got this backwards, and in fact I did. If you put this half the current to program the bead going one way and half of it to go the other way, where they met, there was an additive effect, and the additive amount of magnetism or magnetic field there magnetized that one bead. Now, the problem is you cannot read magnetism. You can only read magnetic changes. So there was another wire that was put diagonally through this bead, and what you would do in order to figure out whether a 1 or a 0 had been programmed there, and think about it this way, a 1 was a magnetism in one direction, a 0 was a magnetism in the other direction. And so what you did was, in order to figure out whether or not you had a 1 or a 0 programmed onto this bead, you simply programmed it as a 1, and you watched this sensing wire. And if the magnetism of this bead flipped, it changed, you'd get a pulse on this sensing wire. And so in order to read a value, what you did was you just simply programmed a bunch of 1s, and wherever there were pulses, you knew there were 0s, and you had to put the 0s back there. So, kind of tedious. Let's talk about storing data with these logic gates instead, because remember, the logic gates, which are based on transistors, can be made much smaller. Let's take a look at that. Now, the idea is this. What we've got is logic. All right. Now, in order to store something, in order to maintain a value that's in here, we need to take the current value, the output from this logic circuit, and be able to put it back in. All right. So there's this idea that in order to store something, I have to know what's being stored. So the circuit, the final circuit, actually has to have this feedback. Now, the very simplest way to do this would be to take well, let's just put 2 inverters and have our feedback like that, right? So if I've got a 1 coming into this inverter, then it flips to a 0, and then it becomes a 1, and that 1 comes into the back end of the first inverter. We've stored a bit. Now there's a problem with this, and the problem is that, well, I can't program it. I can't set the value. If, for example, I try this, maybe, I've got a logic 1 headed back around this way, and if I want to instead store a 0 there, I put a 0 here. What's the voltage going to be at that point? Well, 1 plus 0 is a half, right? And the half is not really a binary value, and in fact, that voltage level is going to not be enough to change this to a 0, nor is it going to be enough to keep it at a 1. So that's really not a very effective way to store a bit. So let's take a look at a gate that we are familiar with. If you remember, we have this thing called a NAND gate. So a NAND gate is the inverted output of an AND gate. And so because an AND gate only outputs a 1 whenever both inputs are a 1, then the NAND gate only outputs a 0 when both inputs are a 1. And you've got a truth table that looks a little bit like this. What I've got is kind of almost an inverter that I can enable or disable. For example, if A is equal to a 0, then the output is always going to be a 1. This is going to be critical whenever we start talking about how to program this circuit. If, however, A is equal to a 1, the output is the inverse of B. So let's see if we can't take advantage of this. Now, let's redraw our circuit. In fact, I'm going to redraw this a little bit different. What I've got are my inverters. Remember, this is the way I wanted it to work. Instead, I'm going to put these 2 inverters side by side. And the output of one inverter goes into the input of the other inverter, and vice versa. So there's our little circuit where we've got the inverted value going into the inverter to become the original value, be inverted, and so forth. All right, this little figure 8. What I'd like to do is redesign this circuit so that instead I'm using the NAND gates. So I've got both my NAND gates pointed in the same direction. The output of one NAND gate is going to come around and go into the input of the other NAND gate, and vice versa. Now, if you recall from the truth table, what we said was that if one of the inputs is held to a logic 1, and I'll redraw this truth table over here real quick, just to give you a refresher. So we had A NANDed with B. So if A is being held to a 1, the output of our NAND gate is the inverse of the other input. So I'm holding the one input to a logic 1. The output of this NAND gate is just like an inverter. So these two expressions are actually equivalent. We've added a little bit, added some transistors, but what we're going to see is that these extra inputs give us the ability to store a specific value. In fact, let's take a look here. Real quick, let's just change one of these inputs to a 0. Now, by changing this one input to a 0, I look over here at my truth table. If that one input is a 0, regardless of what the other input is, I'm outputting a 1. So I know a logic 1 is going to be output there. That 1 also, not only is it going to one of the outputs, but it's also being routed around to the input of this other NAND gate. And I've got 1 NANDed with 1. 1, 1, the output's going to be a 0. And that 0 comes back around to be the input of the other NAND gate, which, of course, once again, we said regardless of what that guy is, we're going to be outputting a 1. But now I've got 2 zeros here. Now, what's really cool about this is that if I now release this and put it back to this hold state where it's working like an inverter, now I still have 0 inverted to a 1, which comes back around, 1 inverted to a 0 comes back around. Now I've got it stable. So let me show you exactly what just happened. What I said was, or what I showed was, that by placing a 0 on the input of one NAND gate forces that output to a 1 and forces the other NAND gate to output 0. Kind of neat. Maybe, maybe not. Let's try this again, except this time what I'm going to do is I'm going to place a 0 on this input. Now, by placing a 0 on this input, if we look at our truth table over here, now going into this NAND gate, I've got a 1 and a 0. 1 and a 0. That's going to output a 1. So we know that this guy is going to automatically get forced to a 1. All right. Now that 1 comes back around here, goes as an input to this NAND gate. Now I have 1 NANDed with 1. 1 NANDed with 1 is going to output a 0. That 0 comes back around, goes into this NAND gate. And we've got a stable circuit. Nothing's changing now. Now I can take this 0, I can get rid of this 0, put a 1 back on here, and now 0 NANDed with 1 gives us 1. That 1 comes back around here, 1 NANDed with 1 gives us a 0, and we've got our inverter circuit again. So it's almost as if I've got two push buttons. I've got a push button for the input of this NAND gate, which I'm going to make it, when I press the button, it turns to a 0. Or I've got a push button on this circuit. When I push that button, it goes to a 0. And so all I need to do is, if my fingers are off the button, this acts like this inverter feeding an inverter circuit. But if I push the button that forces a 0 here, it's going to force a 1 here, which is going to store a 1 on this input, and this guy is going to automatically have the opposite value due to this inverter-like behavior. Now, what happens if I push the button that makes a 0 go here? If I push the button that makes a 0 go here, then this guy becomes a 1. That 1 feeds around here. I've got the 0. I've got the inverter circuit again. I take my finger off the button. Now what I've done is I've placed a 0 here and a 1 here. Now, this is called, this circuit has a name, and it is referred to as the SR Latch. Let's in fact try and get a truth table for this so we can get an idea of the overall operation of this SR Latch. So this is the SR Latch. Now the SR Latch has as its inputs S bar and R bar. Now we talked in a much earlier lesson about the placement of a bar over an input. We referred to this as an active low signal. Now if you don't recall, the definition of an active low signal went something along the lines of this. If the signal is a logic 1, it is idle. It's not doing anything. It's not affecting the circuit at all. But if the S bar input is a 0, if the active low input is a 0, then it's affecting or it's activating the circuit. So what I'm going to do is I'm going to create another truth table here, and I'm going to have S bar and R bar. These are my inputs to the circuit. The outputs, well, we're going to use another letter, a new letter. We're going to use the letter Q. Now, Q, what Q identifies is the stored value. All right? Whatever is stored in this bit, whatever bit is in this box that we're storing, we can find at this Q. Now, because of this circuit right here, remember the inverter chasing the inverter, then this input right here should always be the opposite of this this output here should always be the opposite of that output. So this guy is going to be labeled Q bar. So I've got Q and Q bar, and those two are always going to be in proper operating mode, the opposite of one another, all right? Now, if I've got these two inputs, S bar and R bar, that means I've got 4 possible combinations of 1s and 0s. We just need to figure out which does which, right? what we're going to do is we're going to go through the rows of this truth table. We're going to skip over this one for a moment because it's kind of an unusual case. What we're going to do is this row first. So we're going to put a 0 on S bar and a 1 on R bar. Now, as we said before, if you put a 0 on any of the inputs of a NAND gate, you're going to get an output of a 1. So we're going to have a 1 on Q. Now, that 1 is going to come around here, and in fact, let me go ahead and erase some of this so it's not confusing. All right, so what we've got here is a 0 on S bar, a 1 on R bar. The 0 on S bar is going to put a 1 on the output of this NAND gate. Q is going to be equal to a 1. That 1 comes around here, and I've got 1 and 1 into these inputs of this NAND gate. 1 NANDed with 1 is going to output a 0, and Q bar is a 0. All right. So putting a 0 and a 1 on S bar and R bar respectively outputs a 1 on Q and a 0 on Q bar. As we saw also earlier, if I swap these, if I put a 1 on S bar and a 0 on R bar, then what's going to happen is that the NAND gate that's having R bar as its input, that guy is going to have a 1 on its output. And we'll have that 1 coming around here going into this NAND gate. 1 NANDed with 1 is a 0. And so we'll have a 0 on Q and a 1 on Q bar. All right. Now, as we showed before, either of these states, if I go from this state to having a 1 on both inputs, both S bar and R bar, then what I've got is this circuit right here, and it's simply going to store whatever was last placed on those inputs. So if I've got 1 NANDed with 1, if I had a 0 on Q and a 1 on Q bar, the 0 comes into this NAND gate. 0 NANDed with 1 gives us a 1, so we keep the value of 1 on Q bar. Q bar is going to come back. There's going to be a 1 here. It's going to be 1 NANDed with 1, which is going to output a 0, and we're going to keep that value on Q. The same would be true if we had the opposite, right? So what we're looking at is this 1, 1 is whatever the old value of Q, and I'm going to refer to that as Q naught. Whatever the old value of Q was, it's going to stay there. The previous value of Q, as long as we don't go or visit either of these states, we're going to be maintaining that bit. So when we go to this state, we're going to be maintaining whatever the last value that was placed on Q was. So whatever the value that was on Q, that's going to stay there. And whatever was on Q bar, that's going to stay on Q bar. And so what we've got are these bottom 3 rows of the truth table. This row right here sets to 1. It sets Q to 1. And Q bar is just going to be the opposite. This row right here resets Q to 0. All right. So we've got sets Q to 1 or resets Q to 0. See the S and the R? There you go. That's where the name SR Latch came from. We're either setting or resetting the value that was on Q. So what we've got is a very simple circuit where if you put 1s on both inputs, S bar and R bar, it's going to act like this inverter chasing an inverter circuit. And whatever is stored on Q stays on Q, and the opposite is going to be on Q bar. If I put a 0 on S bar, what it's going to do is force Q to be a 1. That 1 is going to come around to this lower NAND gate. 1 NANDed with 1 is going to be a 0. That 0 comes around here, and it's going to hold that 1 on Q. Then putting this back to a 1, we go down to the save state, and this is just going to keep or maintain that value on Q. Similarly for R bar, if I put a 0 on R bar, then what I'm going to do is force Q bar to a 1, which makes Q a 0. Putting a 1 back here will make it so that it'll hold whatever the last value was. What about this one last state, this 0, 0? And by the way, let's go ahead and name this state. This is basically, I'm just going to call the stored state. So whatever was on Q is going to stay on Q. All right. This state, what about that one? Well, Turns out that if you put zeros on both S bar and R bar, the world is not going to come to an end. We're going to have the circuit is going to be just fine. What's going to happen is a 0 going into the inputs of both of those NAND gates is going to output a 1. So you're just going to have two 1s on the output. The problem is not putting two zeros at the same time. The problem is what happens when you take them off. And in in trying to figure out how this behaves, how this SR latch behaves, what you're looking at is if I go from 0, 0 to 1, 1, there's one of three conditions that are going to happen. And picture this with your fingers on the button, right? All right, so if I got my fingers on both buttons at the same time, and I've got a 1 on both Q and Q bar, if I try to take my fingers off both buttons at exactly the same time, the exact same instant. Well, you may think that you're taking them off at exactly the same instant, but one's going to be just a hair faster than the other. We don't know which one, though. And the same is true in electronics. Due to propagation of these signals across the wires, one's going to be just a little faster than the other. And so in passing from this state to this state, and going from the 0, 0 state down to the stored state, we're going to actually pass through one of these two states first, right? So if we pass through the state, if R bar turns to a 1 before S bar does, we're going to pass through the sets to 1 state before going here, and we'll have a 1 on Q bar, Q naught, or excuse me, we'll have a 1 on Q. If, however, S bar changes to 1 before R bar changes to 1, we'll pass through the resets to 0 state briefly first. By doing that, what ends up happening is we're going to have a 0 on Q, and the 0 will be stored. So there's one of two possibilities. We either pass through the set state or pass through the reset state first. That really kind of makes it so that even if we tried to bring them both up from 0, 0 to 1, 1 at exactly the same time, it's unknown what the actual destination was going to be. Did we end up storing a 1 here, or did we end up storing a 0 here? The other possibility is maybe you really did do it exactly at the same time, and both inputs, S bar and R bar, both turned to 1, 1 at exactly the same time. Well, if we had a 0, 0 on these inputs, then both of these outputs are 1, right? If both of these outputs are 1, then those 1s come around into the inputs of these NAND gates. So I've got a 0 on, and in fact, let's just go ahead and get rid of any ambiguity here. If we have zeros on S bar and R bar and 1s on the feedback, then when I change this from a 0, 0 to a 1, 1 at exactly the same time, both of these NAND gates will have all 1s at the input. All 1s at the input output a 0. So those two zeros come back, they race each other back, and they both get to the NAND gates at exactly the same time. Zeros input to the back end of this NAND gate turn the output to a 1. Those 1s race back. Now we've got all 1s at the inputs. They both turn to a 0. They race through. Both become zeros. And so what you've got is this oscillation. They're going to flip back and forth between 1 and 0 and 1 and 0 and 1 and 0. And until one of the signals beats the other one back in order to pass through either the set state or the reset state, you're going to get this thing in oscillation. And the oscillation is not good. Number one, you ain't storing anything, right? But number two, it actually could damage the chip. All right, so we call this state right here undefined. In other words, the behavior of this circuit at that point is not defined, and we can't count on it to behave properly, especially when going from a 0, 0 to a 1, 1. All the other cases, if we're passing through the sets or resets state first, we know what the output's going to be. But if you try and jump from here directly down to here, we're going to lose whatever, we're not going to know what the outcome's going to be. All right. Now, in the next lesson, we're going to actually talk a little bit more about storing a single bit, but we're going to use a slightly different component to do it. This SR latch is, once again, capable of storing a 1 or a 0 based on the control lines S bar and R bar. But the problem is, it can get a little bit complicated to control that type of a circuit from our processor.